Hello, Professor. I'm going to be presenting uh, a demonstration of my Lab 2. So the Lab 2 is about a design and implementation of a fault-tolerant distributed system of dynamic scaling. This is my table of contents. First, we have the formal specification, which is created according to the requirements you set out in the document. So we have our aggregates here, the client, the, the cyclic distribution queue, Q1, P1, the, the first series of layer of processors, the distribution device, the second tier queues, and the second tier services. And then we have the connections, which is the client to Q1, Q1 to the processors to the distribution service, distribution service to the second layer of queues, and then the second layer of services, and then back to the client. Um, our predicates are the input signal, which represents an increment signal to an aggregate, the output signal, the state, the internal event, and the auxiliary conditions. So here are the production rules. I've written them in detail. We have the request submission, the cyclical distribution of the incoming requests, um, the prior to queue processing uh, inside of the queues. The processors take take the tasks based on the priority of each task and whether there's an empty service at hand, empty processor at hand. We have type-based routing, which obviously the higher priority type of tasks are routed first. Um, and then we have this forward attempt. Forward the request from the second tier queue to its corresponding processor when it's available. So it's just waiting in the queue, and then the processor might reply with a busy reply, uh, and then which results in a failed connection. Um, so, for example, in case of failure, this might happen. And then we have the processing, um, which is standard. And then we have a service completion rule where it dictates how the service when the service is completed. And also we have failure events because you wanted us to implement this, and I coded a probability of 5% to check whether there's a failure event happening. And if there's such an event, there also needs to be a recovery event coming after to see when the resource can come back up online. I also implemented like a scaling detection such that let's say there's like 50 task ones, then in that case it would create more resources of the relevant processor uh, processing service. Yeah, and there's a response collection from the client to the second layer of processor nodes. And then if there's a success, we return that. A request to be marked as success when 3 responses are collected before timeout. And we might also have a timeout option because if it waits in the queue for too long, it removes the request from the queue, which means there must have been a problem. So the architecture of the system is it's detailed here, but I think looking at the image is very easy. We have a distributed request processing system with the clients. They go to the cyclical distributor. It distributes round robin and also based on priority of the tasks. And then we have type-based distribution, um, which go to type-specific queues, and then the tasks are handled there. And after the second layer of processing, they're back to the client. So I also implemented this dynamic behavior, um, these dynamic behaviors. So we have failure simulation and recovery. So we simulated some failures in the second node of processors. And this is also an adjustable, there's a config file that we can adjust this in. So now it's 5% and the recovery period of 3 to 8 seconds. Um, I implemented dynamic horizontal scaling, which if there's too many requests, and this it calculates this by looking at the average depth of the queue over three measurements or every second, and then it's if it's above the average of the last 3 seconds, it creates a new node to handle the increased demand. Yes, adaptive request queuing, prior to dynamic scheduling, obviously. And here are the metrics. Obviously, these can be changed. Right now, it's around 49, 42%, but this depends on. I'm showing the metrics of these two clients, and it depends on the failure rate of the processors in the second layer. It depends on the failure check rate, how often we check for whether there's a failure or not, and it depends on how often there's a request, the request interval from the clients, and how many requests there are. It depends on all of these things which are in the config file, which I'll show you in a second. And this is it. And I will show you. Here we go. Um, so I will try and run it. It should take no time. So this is if you can see. Yeah, these are all different requests. There's I'm testing with around 100 requests, so there's a lot of logging happening. um, but it finishes in less than 30 seconds. In the meanwhile, I will show that these are the you wanted us to show the safety and liveness properties of the system we created. So for the safety properties, we have priority ordering preservation, so that higher property requests are never delayed behind lower priority requests. And in the problem specification, it's there as well. And the implementation is obviously it looks at the list, but it also checks the highest priority first. So that's how it's handled. Um, and then it's safety because obviously the system needs to handle the higher priority things first. Some. And for the second safety priority, safety property, we have request uniqueness and no duplication. Each request has a unique identifier and is processed at most once by certain. So no request duplication occurs. We do this by giving a unique identifier. They all have their own IDs, each request, such as this one, for example. And then for the third one, we have type-based routing correctness. Distribution node D routes based on request type. Type to queue mapping is never violated. So each processor handles a different type of request in the second layer. And for the liveness property, we have every request termination, every submitted request eventually reaches a terminal state. No request hangs indefinitely because we have, and this is done by implementing a timeout as well as, yeah, the timeout is the most important part. Otherwise, it might be stuck waiting forever. Timeout is very important here. Um, and for the liveness property set number 2, we have failure recovery. When the node fails, it eventually recovers and resumes processing requests. Of course, since this is a simulation, we have to code this in manually. Normally, it would be a very complicated process, but on this one, it's just a simple function that tells it to come back online after a random time down duration that's picked. And after this one, we have the liveness property number 3, scaling response to overload. So this is the one I talked about before, where if the system detects a persistent overload, high queue depth, above the average queue depth over the last 3 requests, then it creates a new resource to handle this heavy load. Yes, and so here's the code and the results. So here again, we have client K2 summary, 42% success rate. As you can see, sometimes there's a timed out request. If there's a busy processor, it requeues the service. But if it keeps requeuing, then after a while, some of them will time out. And if I change some of these config files here, for example, right now the max wait time is 5 seconds. If let's say I increase this to 10 seconds and I run it, I should have a much higher success rate. Maybe I could show that as well. And that should be it for now. I will show this and then I will end the video. Hopefully it wasn't too long, Professor. 10 minutes. Okay, it was a bit too long. And I also believe I showed the formal specifications, and let me check. I showed the formal specification, the implementation of the simulation model, the introduction of dynamically changing elements. This is for my system. This is the increased amount of um, processors based on need. Of course, there's a lot of randomness in node, but as you can see, it's higher than 42%, 53%. But this one is, for example, 40%. It's very since it's chance based, probability based, it can vary a lot. But over time, as you adjust these stats to reflect your real system, it might be able to give a more successful simulation result. Thank you, Professor.